In this chapter, we are going to look at two functional groups, carboxylic acids and esters. Carboxylic acids occur in many household items. For example, vinegar here contains the carboxylic acid acetic acid. Aspirin contains acetyl salicylic acid, which is a carboxylic acid. Vitamin C is ascorbic acid. Lemons contain citric acid, and spinach contains oxalic acid. The tart flavor of foods that taste sour are generally caused by the presence of one or more carboxylic acids. So many of these things can kind of taste sour to us. The tart taste of apples is caused by malic acid. Now, so these are found pretty frequently in foods. The ester functional group is also found pretty frequently in familiar flavorings. These esters are represented kind of with this C double bond O R group here, and you can see the different types of esters and the flavorings that they have. And so we find these particular functional groups in food and food products pretty frequently. So our first screencast is going to talk about carboxylic acids, and our second screencast is going to talk about esters. So without further ado, let's jump into carboxylic acids. So when we think about the carboxylic acid, the functional group of the carboxylic acid is a C double bond O OH, and this is called a carboxyl group. And it's tricky because there's a couple different abbreviated forms that you need to watch out for. It can be drawn as COOH, or it can be drawn as CO2H. So we just want to make sure that we are looking for that. Now, carboxyl containing compounds are found pretty abundantly in nature. And so here's some examples here. When we look at these, we can see there's lactic acid here. This is formed in muscle cells during vigorous exercise. There's citric acid, which is shown here. That is really an important intermediate in cellular energy production, but it's also present in citrus fruits. So we'll talk about citric acid again when we get into biochemistry. Now, when we look at these particular groups, I want to look at two of these particular groups that we run into a lot. And one is vinegar, which is acetic acid, which is shown right here, and the other are fatty acids. So just because of their abundance in nature, carboxylic acids were really among the first organic compounds to be studied in detail. And so there was no systematic nomenclature was available. So the acids are usually named after some sort of familiar source. So for example, when we talk about acetic acid, which we know is vinegar, okay, that was named after the Latin word acetum, which means vinegar. Then butyric acid, which was on the previous page, this occurs in rancid butter, but it also is named after the Latin word for butter, which is butyrum, because that was found in the rancid butter. Many of these common names are still used today, but we also will use a systematic nomenclature to name them as well. Now, I also want to talk really briefly about carboxylic acids with long hydrocarbon tails, and we're going to abbreviate carboxylic acid as Ca. So carboxylic acids with long hydrocarbon tails right? Which are generally about 12 to 20 carbons, are called fatty acids. We're going to talk about these again in chapter 19, right? And the reason they're called this is because they were first isolated from fats. Okay. These acids are almost completely known by their common names. We have two different divisions here when we talk about fatty acids. We can have saturated fatty acids where they're completely saturated with hydrogens, or we can have unsaturated fatty acids where they contain double bonds. If it's a monounsaturated fatty acid, it contains one double bond. And then if it's a polyunsaturated fatty acid, it contains more than one double bond. And so we find these pretty frequently in food, but I want you to pay attention to this carboxylic acid functional group here. So these are natural carboxylic acids that we find in food and just in common household items. Now let's talk about how to name these carboxylic acids. To name the carboxylic acid, we can use an IUPAC system. We can use their common names, but IUPAC systems a lot of times are easier. The longest carbon chain has to include the carboxyl group, and you need to find that and number it. So, for example, we're going to look at this guy together. Okay, so when we look at this guy, this is our longest carbon chain that contains the carboxylic acid, and it has 3 carbons. Because it has 3 carbons, we're going to use the parent hydrocarbon name of propane. We are going to drop the ANE of the hydrocarbon and add oic acid. So that's OIC acid. So this is propanoic acid. When we look at this, we start numbering from the carbonyl carbon here. So this would be 1, 2, 3. Because it's always going to be in the 1 position, if there's just one of these, we do not need to include a number. Let's look at another example. Let's look at, for example, this guy. In this example, our longest hydrocarbon chain is here that contains the carboxylic acid. When we count, there are 1, 2, 3, 4 carbons, and so that means it's going to have the base of butane. And so we drop the E ending and add OIC, so it's butanoic acid. And then we see that there's a substituent, and that's bromine, and it's on the 3rd carbon. And so we would name this 3-bromo-butanoic acid, where we start naming from that carbonyl carbon. Now, if you have groups that are aromatic, so for example, if we have this molecule here and we're asked to name it, these names are derived from the parent compound, which is benzoic acid, which looks like this. And so we are going to use that as our base name. And so when we come over here and we look to name this, we say, okay, hey, look, I can recognize that the benzoic acid is right here, and it's the same as this, okay? And so we can say, look, we know that's benzoic acid. And then we count using the place where the benzoic acid is attached to the aromatic ring as the 1. And then we go 2, 3, 4. And we get 3,4-dimethyl benzoic acid. And so these are the ways that we name carboxylic acids. Let's look at some of their physical properties as well. When we look at their physical properties and look at boiling points here in this table of compounds that have similar molecular weights. So these molecular weights are the same, and these are the classes that they're in here. One of the things that you can notice here is that carboxylic acids have the highest boiling point, so that we've studied so far. So when you compare the classes, carboxylic acids have the highest boiling point of the organic classes that we've studied so far. So when we look at this, a lot of times we want to ask why. Why are carboxylic acids have such higher boiling points than, say, alcohols, which are really similar, right? So alcohols contain the OH, they just don't contain the C double bond O. So what is special about this C double bond O that increases the boiling point? Well, one of the things that is special about it is that carboxylic acids will form these dimers, and basically dimers are just two identical molecules that are bonded together. And those hydrogen bonds between those COOH groups, right, causes really high boiling points. So the formation of the intermolecular, and let me spell out intermolecular there. And intermolecular just means between two atoms. Cause high boiling points. Okay. And specifically, that hydrogen bonding creates dimers, right? And this here is an example of a dimer. Okay. Additionally, that COOH group is very polar. And so that, of course, increases the dipole-dipole interactions. Now, when we look and compare the boiling points here, this is a chart, and I love charts, but maybe you love graphs. And you can see the graphs here as well. For these simple aliphatic compounds, the boiling points usually increase in the order of alkanes and ethers, which are about the same, then aldehydes and ketones, which end up being about the same, right? But you can see here where there's those aldehydes and ketones. Then we have alcohols, which are shown here, and then carboxylic acids. I also want to point out that when we talk about these intermolecular hydrogen bonds and we compare it to alcohols, right? Alcohols only form one hydrogen bond, whereas carboxylic acids form two hydrogen bonds. And that's one of the reasons that boiling point is increased there. Now, carboxylic acids, I want to draw your attention back up here one more time. Carboxylic acids of low molecular weights tend to be liquids at room temperature, and they generally have really characteristic sharp or unpleasant odors. As the molecular weights get higher, they are solids at room temperature, and you can think of some of your waxes and things like that. And so I want us to look at that in another chart. So this is the other chart that I wanted you to look at. And so carboxylic acids with low molecular weights are liquid at room temperature. And we can see the, when we look here, particularly at this table, this increases molecular weight this way because it's going to increase as the number of carbons increase. So this would be our lowest molecular weight carboxylic acid, and then this is going to be the highest one that we look at, particularly in this table. when you look at this, butyric acid, which is shown right here, is a component in perspiration and is partially responsible for the odor of locker rooms and unwashed socks. And so that what we're going to see there is that it's going to be a liquid. It's pretty soluble. Then as we increase our number of carbons, we are going to see that at room temperature, these are going to be solids. For example, stearic acid down here, right? That's going to be a solid, and it's generally mixed with parafilm to make the wax that's used in candles. So basically what we have here, right, is down to about there. We've got liquids at room temperature, and then here we've got solids at room temperature. I also want you to notice here that as the number of carbons increase, we're now insoluble in water. So we're not going to mix with water because the more nonpolar portion here of the molecule really takes over compared to the polar portion. So let's put some of that into words, right? We know that the COOH group can hydrogen bond with water. And if the length of the R group is not too large, that means the carboxylic acids will be water soluble. So those low molecular weight acids are going to be really soluble in water, but then as the length of this R group here increases, then the water solubility decreases. And basically, we always love to ask where the cutoff is. Carboxylic acids with 8 or more carbon atoms are not soluble in water. And so that means they're not gonna dissolve in water, they're not gonna mix with water. They would separate out like oil and water that you would see. And so we would describe these as insoluble in water. Now, organic compounds can be arranged according to increasing solubility. So hydrocarbons are the least soluble. Okay. Then we have ethers, aldehydes and ketones, alcohols, and then we end here with carboxylic acids, where these are the most soluble. And the reason they're the most soluble, and this is the same trend for increasing boiling point, and the reason is also the same. Carboxylic acids can form 2 hydrogen bonds, and so that increases the boiling point, and it also increases the solubility because now you've got your carboxylic acid that can form 1 hydrogen bond here with water and another hydrogen bond here with water. So hydrogen bonding really influences our boiling point and water solubility. So we've talked about carboxylic acids, we've talked about what they are, we have talked about some of their properties, and now we're going to talk about some of their reactions. The most important chemical property of carboxylic acids is the acidic behavior, which is just implied in their name. The hydrogen that's attached, which is shown kind of right here, to the oxygen of the carboxylic acid group, is what gives the carboxylic acid its acidic character. And so a lot of times we call that the acidic proton, right? Because in a proton is just, I want to remind you from your acid chapter, H+. Okay, and so what can happen here is this proton can be transferred to this H2O to form H3O+, and we end up with a carboxylate ion. And this is just because we've taken away the H+ here, now this oxygen has 6 electrons on it, and so it ends up with a negative charge. I want us to look at a specific reaction. So for example, if we put vinegar in water, so this is acetic acid, and we added water, this will form and I'm going to draw my electrons in, O- there. And we call this the acetate ion, and it's going to form H3O+. Now, I want to point out that generally carboxylic acids behave as weak acids. And so what this means is that in equilibrium, so once this reaction has come to equilibrium, that's why we have arrows that go both ways, we only end up with about 5% of the acid in the H3O+ form in the acetate ion, and about 95% where it stays as the acetic acid. So it's what we say is it's only about 5% dissociated. And basically, I want to remind you, the more H3O+ that is formed in reactions like this, the more acidic the compound is. Okay. Now, one of the things to kind of be aware of is that the pH of the solution determines the form that the carboxylic acid exists in. And this is due to Le Chatelier's principle. For example, at a low pH, you have more H3O+. And so because you have more H3O+, it shifts the reaction to the left. So you have less acetate ion because you shifted to the left. If you are in a more basic environment and you have less H3O+, then the exact opposite happens. It's going to shift to the right. Now, what does this mean for us? Well, at a pH equal to 7.4, which is your normal body fluid pH, you are going to get that carboxylate form. And that's going to be the majority of what you see, and so we say that that predominates. So a really good example of citric acid in body fluids is often referred to as citrate, and we'll see this later in our biochemistry chapters. Now, this is as we mentioned, this carboxylic acid is an acid, and so it does not surprise us that it would react with bases. And so it does react with strong bases, and it pretty readily forms salts. And so you can see here where we've got the negative charge, and then we now have a metal ion that comes along with that to form the salt. And salts are just combinations of two charged species that are held together with this charge. And a lot of times salts are your metals and your nonmetals. So if you think of like NaCl, this has Na plus and Cl minus, and we call that a salt. Here we have the Na plus, and then this whole complex is minus. This is a generic reaction where R stands for the rest of the molecule. Let's look at a specific reaction. So for example, let's say that we've got benzoic acid here, and it reacts with potassium hydroxide, which is a strong base. I want to remind you your strong bases here are your group 1 and 2 metals with OH that's bonded to them. And so then what happens is when we go to predict this product, what we do is we look at it and we say, okay, hey, look, we've got C double bond O, O, and what's happening here is that we are removing this proton, and then it reacts with the OH minus to form the water here. So I know that my proton is going to be gone, and so I'm going to have a negative charge now. And then whatever the cation is, which is right here, and remember cations have positive charges, that's now going to be with my negative charge. Then I know I also form water each time. Now the name of this is potassium benzoate, and I want to talk to you now about how we would go about naming some of these salts. So when we go through and we name the salt, you name the metal ion first. So for example, if we have CH3, C double bond O, O minus, Na plus, okay? We name the metal ion first, and so we know that name is going to be sodium because that's our metal ion. Then we need to change the ic ending of the acid name to the ate, and so this means you have to think about what the structure of the acid was. And so the structure of the acid here was CH3, C double bond O, OH, and this has two names. It's got a common name, which is acetic acid, and then it has a IUPAC name, which is ethanoic acid. And so what you do is you drop the ic ending of the name, whichever one. So we're either going to drop the ic ending of the acetic acid or the ic ending of the ethanoic acid, and you add 8 to it. So this could be called sodium acetate, where we've added the ATE right here where the ic acid was, or it can be called sodium ethanoate, where the AT is added where the ic acid was. Now, even your long chain acids can be solubilized by converting them into their salts. So for example, stearic acid is insoluble, but if we add sodium hydroxide to it, which is a really strong base, you end up getting sodium stearate, which here is soluble. When we look at this, I want you to notice that it's named in the exact same way. It's stearic acid. We drop the ic acid component right here. And then instead we add the ATE component there, and we are going to tell the name of the cation as in the front. So even the larger ones are named, carboxylic acids are named in the same way. Now, let's talk about a few useful carboxylic acids. A number of acid salts are really important around the home. So, for example, right, we've got sodium stearate, right, and other sodium and potassium salts of long-chain carboxylic acids are used as soaps. So if you ever go to a craft fair and you see somebody making soap, they're adding lye to it, and that is a strong base. And so they're doing the reaction on the previous page to make soaps. You can have calcium and sodium propanoate. And these are used as preservatives in baked goods. And they keep them from molding. Sodium benzoate is also a preservative. Right? And so this is also used as a food preservative in baked goods. Right? But it's also like in ketchup and carbonated beverages. And then we also have zinc 10 undeclinate, and that's used to treat athlete's foot. So we see lots of these carboxylic acid salts around and are used pretty frequently in our everyday lives. Now, we also have another carboxylic acid salt that's used so frequently because it forms a buffer solution. So if you have a mixture of sodium citrate and citric acid, it's widely used as a buffer. And buffers just control pH. And what they do is they keep the pH from fluctuating widely. Okay, so they'll control the pH. They'll keep it close to where it should be. So, products that are sold as foams or gels, like jelly, ice cream, candy, whipped cream, only maintain their desirable characteristics at certain pHs, and that's controlled by this citrate buffer. So this buffer can be found in jelly, ice cream, candy, some candies that kind of have that whipped texture, whipped cream, because the pH is really critical to keep these textures. Now, this same buffer is used in medicines as well, right? And in human blood for transfusions. And so it acts as an anticoagulant, which means it keeps the human blood from forming clots. So it's also used in transfusions. As an anticoagulant. Right? And so it's super important. You can see the structure right here, and it's particularly important in keeping the texture of some of our food products as well. So this ends our discussion of carboxylic acids. In the next screencast, we will look at esters.